So our second talk in this morning session is given by Emil Jeřábek from the Institute of Mathematics of the Academy of Sciences in Prague. And he's going to speak about root finding in TC0 and open induction.
Okay. Thank you. Sorry for the technical problem, but it will be okay now. So here's a kind of a motivation for what I'm going to talk about. So we consider the correspondence of bounded arithmetic theories and complexity classes. So the way the correspondence works is that we have a theory T and class T, and now on the one hand probably total computable functions of T of some complexity, say sigma 1, 1, are functions from the class C or FC, more precisely, and what is this here?
Just, you may need to move away the mouse.
Just move the mouse a little bit.
Away from the slide.
Okay. The theory T can do reasoning using concepts from this class C. So typically it has it can do induction for predicates from C. Or if it's the second order theory, then it has comprehension for predicates from the class C and so on. Usually there are also some kind of minimization schemata and so on, which go on with induction. Then we can consider some form of feasible reasoning. If we are given a natural concept from this class, we can ask what can we prove about this concept using only things which are of the same complexity. So if we just do reasoning which uses concepts from this class C, and if we formalize this, then this really means that we are asking what this theory T, which corresponds to this complexity class, can prove about the concept. And what I'm going to consider in this talk is that we take for this concept P the elementary integer arithmetic operations, addition, multiplication, and ordering. So this is actually the basic language of arithmetic. So we will take the complexity class C, which naturally corresponds to these operations. We will take a theory T, which corresponds to this class, and we will ask what properties about these arithmetic operations are probable in the theory. So first, what is the class and what is the theory? Well, I guess people in the audience actually know what all these classes mean, and anyway, Fwong gave an overview of these small complexity classes in his lecture yesterday, so I'll probably skip over this, but let me just stress that in this talk all circuit classes are assumed to be uniform. If you look at these arithmetic operations, then addition and ordering are very simple, and they are already in IC0, whereas multiplication is in the class TC0, and it is in fact TC0 complete under AC0 Turing reductions, which means that the class we should consider as the natural class for arithmetic operations should be TC0. here is just a reminder of first the definition of uniform TC0 and of the fact that it is a fairly natural and robust complexity class which admits several definitions coming from disparate areas. So the usual definition is that it is a log-type class of languages definable by log-type uniform families of constant depth polynomial size threshold circuits or circuits with majority. But it can also be defined using so-called threshold Turing machines, the class of languages decidable in logarithmic time using constant limit thresholds. And in descriptive complexity, it can be defined as classes of finite structures which are definable in first-order logic with majority quantifiers. Now, TC0 can contains addition, multiplication, and ordering, but it can actually do much more. First, well, it also contains iterated addition, but it's not terribly hard to see. What is more important and took quite a long time to prove was that in uniform TC0 we can also do integer division and iterated multiplication. And we can also do the same arithmetic operations on the rationals instead of integers or even Gaussian rationals. Using iterated addition and multiplication, we can also approximate compute approximations to functions given by power series. So we can sort of approximate sine or logarithm, case roots, and so on. And we can do other stuff apart from arithmetic, like for example sorting can be done in TC0. So TC0 is very much the right class to consider when we ask about basic arithmetic operations. So this is the complexity class, and now what about the theory? So the basic theory for TC0 is this theory VTC0, which we have also seen yesterday in Fuang's talk.
So most common
the most common means that for various reasons you can also consider other theories, and you will actually see one in the next slide or something. But generally speaking, the VTC0 is the TC0 theory which is considered in the literature. Or well, there are, for example, first-order theories corresponding to TC0, like this. What's the name? Delta B1 CR. But that's actually RSOV isomorphic to VTC0, so we can consider these it to be the same theory. Anyway, so let me just remind that the VTC0 is two-sorted bounded arithmetic in the Zambella style. So we have one sort for unary integers, and we have arithmetic on them. And we have the second sort is for finite sets of these unary integers, which we can also interpret as encoding binary integers or binary strings. And we can say that we can find what is the xth bit of a particular binary string or integer, and we have this function which gives an upper bound on well, basically we can compute the maximum number in the finite set. And apart from some basic axioms, we have comprehension for bounded first-order properties, and that will be the theory V0. And what makes this theory correspond to TC0 is that we have this axiom that says that every set has a counting function, which gives us basically a TC0 complete function, and this forces the theory to correspond to TC0. So the sigma 1 undefinable functions of the theory are the FTC0 functions,
and the theory has induction, minimization, and all kinds of schemata like this for TC0 predicates. Now, so with respect to arithmetic, VTC0 can define all the three basic arithmetic operations on binary integers, and it proves that some kind of universal common properties of them, which can be summarized by saying that it proves that integers form a discretely ordered ring. And now the main question of this talk now is what other properties of these arithmetic operations are provable in say VTC0. More precisely, when I say other properties, I mean first order properties expressible in this language, so we can formulate it in this way, as it is said here, that we consider the interpretation of the theory of discretely ordered ring in VTC0 by these binary integers, and when we ask about properties of the theory consisting of all formulas which are provable under this interpretation in VTC0. Now, there is a sort of annoying catch with this idea that we do not actually know whether VTC0 can even formalize this Hesse-Allender and Barrington algorithm for iterated multiplication and for division. And this would be kind of the most basic property of these arithmetic operations right after these discretely ordered ring axioms. And I actually do not want to go into this issue in this talk, and this is certainly a very important and basic question whether VTC0 can formalize these algorithms, but it's a question for another talk. So what I will do is simply to consider the totality of iterated multiplication as an additional axiom which can be formulated like this, and I will consider the theory VTC0 together with this axiom. And I said I'm interested in what properties of the basic arithmetic operations are provable in this theory, but what I'm specifically interested in is whether the theory can prove some non-trivial instances of the induction schema in this basic language of arithmetic. So the weakest arithmetic theory is with some non-trivial fragment of induction, which has been studied, is this theory I open defined by Shepardson, which consists of the theory of discretely ordered rings plus induction for open formulas in this language. So the question now is whether VTC0 plus iterated multiplication can prove open induction for formulas in this language on binary integers. Now there is this remark here that this open induction here is a for all exists schema, and its universal fragment has been described by Wilkie, and it's included in the theory of Z-rings, which can be axiomatized by saying that we can do division by any standard number. And it's not hard to see that we can actually do this in VTC0. So already VTC0 proves all universal consequences of I open. And so when we ask about probability of I open, we actually ask for witnesses to these existential quantifiers which appear in the axiomatization. Now, what these existential quantifiers actually witness, this is more clear from the following characterization of I open, which is also due to Shepardson, which says that if we have a discretely ordered ring, then it is a model of open induction if and only if it is an integer part of its real closure. So the real closure of the ring is the maximal ordered field, which is an algebraic extension of the ring, and that it is an integer path means that for every element in the real closure we can find something in the original ring which is within distance 1 from the element. We can also formulate it like this, that if we have a polynomial over the ring and 2 points where still in the ring where the polynomial assumes different signs, then we can find a point in the middle where the sign switches when we go from x to x plus 1. So this suggests that open induction is related to some form of root finding, and in particular, if you have an existential formula in this basic language of arithmetic, then it translates into sigma 11 formula in the language of VTC0, and since we know that sigma 11 consequences of VTC0 are witnessed by TC0 functions, it is not hard to realize that we have the following equivalence, that VTC0 proves open induction if and only if for every constant d we can find a TC0 root finding algorithm for say rational polynomials of degree d, such that the correctness of the algorithm is provable in VTC0. And the same thing holds if we replace here and here VTC0 with slightly stronger theories like this extension with the iterative multiplication, or we can add in any true universal axioms as well. So the basic question reduces to this problem whether we can find a root finding algorithm for constant degree polynomials which can be formalized in the theory. So I will first say how can we do this root finding in TC0 at all, and then I will say something about the possibility of formalizing it in VTC0 plus iterative multiplication. So root finding is one of the most popular problems in computer science literature. So there are dozens of various algorithms, and I will not probably go into the details here, but I'll just say that the known algorithm show that root finding for polynomials of unrestricted degree actually is can be parallelized. It is in this class NC, but it doesn't quite give what we need here, namely to get it down to TC0. So, but this can actually be done. So for any constant d, there is a TC0 root finding algorithm for degree d polynomials. And this by itself implies that if we take VTC0 and expand it with all true universal formulas, then this theory proves open induction. Now, the algorithm uses some elementary things from complex analysis. The basic idea is that a polynomial is in particular a holomorphic function, and therefore its inverse is also a holomorphic function and can be locally expressed or defined by a power series. And as we have seen before, we can approximate power series by a TC0 function. So the overview of the algorithm is that we apart from some pre-processing and post-processing steps, we first compute roots of the derivative of the polynomial because we will need them for some reason, and then we identify a polynomial size sets of what I call sample points, which you should imagine as points which are sufficiently such that every root of the polynomial is somehow close to one of these sample points. And for each of these points, we consider the polynomial on a neighborhood of this point. We take its inverse, which is called g here, and we consider the power series which expresses this inverse, and then we just output a partial sum of this power series evaluated at the point 0. So computing a root of f is the same as computing f inverse on the argument 0. Basically, that's the idea. Now there are roughly two things which we need to make this work. One of them is that we need to make sure that the coefficients of this inverse series are actually TC0 computable. And second thing is that we need various bounds on the coefficients of the power series and on the radius of convergence of the series and on the radius of image of this inverse actually. This in particular implies that first when we do this approximation by cutting of the power series at by computing only a finite partial sum of the series, and this will give sufficiently close approximation if we cut it at polynomial many terms. And second, we need to make sure that we can devise this polynomial size sets of sample points which would have the property that every root of the polynomial is actually sufficiently close to one of the sample points, so that it actually is a possible value of this G0. Now, the first part, the TC0 computability of the coefficients, follows from Lagrange inversion formula, which in general tells what are the coefficients of the power series inverting another power series. That is a kind of neat formulation of the inversion formula using residues, which looks like this, but one can actually obtain from it some sort of explicit version, which you have here, where you have here are the coefficients of this polynomial f, and we explicitly compute the coefficients of the power series by some sort of a sum like this. The thing to note here is that here we have a sum over these sequences m2 up to md, which satisfy this condition, and the number of these sequences is basically n to the d. So as long as d is a constant, there are only polynomially many terms in this sum, so we can do this in TC0. We can also do these factorials here by iterative multiplication and so on. So the whole thing here is TC0 computable. Now, and another things are the bounds on the coefficients and the various radii, and I guess I will not go into the details here, but okay, I'm not sure whether the picture is actually readable, but the basic idea is that if we have here we have the polynomial f, and here is the radius of convergence of the series, of the inverse series, which is marked here, and then the range covered by this power series here contains a circle whose radius is a constant fraction of the distance of this point to the nearest root of the derivative of the polynomial. So this is the reason why we actually cared about the roots of the derivative. And this property that this thing here is a constant fraction of this distance enables us to construct this polynomial set of sample points. Namely, whenever we have a root of the derivative, we take intersections points of several lines going through this point, and then circles whose distance from this root will exponentially increase, basically. And then, yeah, and one can get from the bounds on the previous slide that this all sort of works. Now, what about formalizing the algorithm in the theory? Let's say VTC0 plus iterated multiplication. I already said this, the existence of this root finding algorithm by itself gives us the probability of open induction in this theory extended by all through universal sentences. And if we want to get rid of these universal things here, then we need to formalize the soundness of the algorithm in say VTC0 plus iterated multiplication. And the obvious obstacle is that the original proof of the soundness of the algorithm heavily uses various tools from complex analysis, and these are simply not available in bounded arithmetic. So we need to do something else. And as I said, what we basically need to prove the soundness are this Lagrange inversion formula as one thing, and second things are bounds on the coefficients. Now, okay, I'm already running out of time, so I'll just say that we can actually do the first part able to prove the Lagrange inversion formula. The Lagrange inversion formula, it's restated from the previous slide, so looks like here we have these funny sums and products, and here are some coefficients which are somehow modified multinomial coefficients, and here is a product of something, basically the coefficients of the original polynomial. So then the inversion formula as such can be reduced by eliminating these coefficients of the polynomial, and it boils down into this kind of a recurrence equation for these sort of multinomial coefficients. And okay, I'll skip this. And we can prove this identity by induction by proving simultaneously this identity and two other funny identities, and it all somehow works out that that one can like show all these three by induction. So and the induction steps are actually fairly elementary. It's by direct manipulations of these sums and products. So we can formalize this in VTC0 plus iterated multiplication. What we cannot do, or I cannot do so far, are these bounds on the coefficients, but still we can do at least some crude bounds based on the idea that we simply estimate these coefficients here. It's easy to see that they are exponential in these parameters m here. So, and then if we use this to get a bound on the coefficients of the power series, it doesn't quite give the full root finding algorithm, but it's sufficient to in some particular special cases. One of the special cases is that we can compute dth roots of any number. So so VTC0 plus iterative multiplication can prove that well, here it's written for integer approximations. We can approximate the dth root of any binary integer. And the second case where it works is when the polynomial whose root we are trying to find is standard. So that basically means that if we take a standard algebraic number, then we can represent it by or compute its binary expansion by a TC0 algorithm in such a way that that VTC0 plus iterative multiplication proves that this algorithm actually computes the root of the polynomial. So this is written in a somewhat sloppy manner, but you can make this precise. And the question is still whether we can actually prove proper bounds in the form that I needed them for the algorithm, and therefore whether the theory does actually prove the full open induction. So, thank you.
I think we have time for one or two short questions.
So do you have any conjecture on whether I mul falls from VTC 0?
Well, it's really a tough question, but the question is basically whether one can formalize this as Allender-Barrington algorithm in VTC 0, and on the face of it, the algorithm doesn't use any sophisticated tools. It's really just a elementary computation with I don't know, modular exponentiation and so on. But trouble is that the whole analysis is plagued with sort of chicken and egg problems. Basically, in order to prove that their algorithms for modular exponentiation works, you already assume that you have modular exponentiation, and then it also works out. But it's not clear how to do it if you're actually trying to define the modular exponentiation using that algorithm. And the same holds for the main part of the algorithm where they actually do this iterative multiplication. So I don't really know it. It could really be either way.
Any more questions? And let's thank Emil again.